Welcome to Pre-Calculus. Today we will investigate removable and infinite discontinuities in rational functions, focusing on describing function behavior as it approaches discontinuities both from the left side and from the right side. We'll take a look at two examples. So for our first function, we've got both an equation and a graph. Our equation says f of x equals 3 divided by x plus 3. And our instructions ask us to first of all identify any removable or infinite discontinuities, labeling with the coordinates or the asymptotes. Our second task is to describe the graph's behavior from the right-hand side and from the left-hand side using infinity notation. So we want to start off with that first task, just identify any removable or infinite discontinuities. So let's remember how we find those, and particularly how we find them from the equation. So a removable discontinuity is something we see in the equation when I have a cancellation above and below. And the way that I find that type of cancellation is by factoring any polynomial in the rational function. So that would include in the numerator and the denominator. And again, I'm looking for cancellation. So I'm looking for an identical factor in the numerator to cancel with one in the denominator. But if I look at this function, there's really not a whole lot to factor in the numerator or the denominator. 3 is itself, that's a constant. Similarly, x plus 3 in the denominator is a factored linear binomial. So there's nothing to factor, which means no cancellation. And the bottom line here is that there's no removable discontinuity. So here we see a non-example of a rational function with a removable discontinuity. It's just not here. Always a challenge to spell discontinuity. Let me correct that, discontinuity. Once you decide about the removable discontinuity, our second go-to is to identify any infinite discontinuities. So our attention for an infinite discontinuity is really looking at the denominator and seeing where the denominator has a value of 0. So in other words, if I were to plug an x value in, what x value would make my denominator equal 0? So we'll do that. The actual algebra is take your denominator, set it equal to 0, and solve. So we'll do that here. My denominator is x plus 3. Set that equal to 0. And to solve that, that's a real quick solution. I'm just going to subtract 3 from each side. And what that gives me is an equation for the vertical asymptote x equals -3. So it looks like, although I didn't have a removable discontinuity, I do in fact have a infinite discontinuity, and I can see that real clearly on the graph. If I highlight this vertical asymptote in green, I can see that where it's crossing at the x-axis is directly between -2 and -4. And so that definitely is the value -3. So my equation from the denominator matches with what I'm seeing on the graph. So I've labeled the asymptote there to finish that first part. So we've identified and labeled the discontinuities we had. This one has an infinite discontinuity at x equals -3. Once I identify that, my second task is to describe the graph's behavior from the right-hand side and from the left-hand side. So we'll write that end behavior, and we'll start from the left. So the way we would write that, I'll go ahead and say this is end behavior from the left. So we would say as x approaches, and the number that it's approaching is the vertical asymptote, so -3. But I want to say from the left, so that's that superscript of the minus sign. That says from the left. And then to decide what the function's doing in terms of its y value, I can look at the end of that graph on the left-hand side of the vertical asymptote and just ask myself, where is that part of the graph tending towards in terms of y? So I see that that side, it's just plummeting towards kind of the lower reaches of quadrant 3. and that's taking it towards negative infinity in the y. So the way I'd complete that end behavior statement is that y approaches negative infinity. So I'm using the graph, but then I'm describing it in an infinity notation. We'll repeat that looking on the right-hand side. So we would write it very similarly as x approaches -3. To say this is from the right-hand side, I would put the superscript of the plus. And again, I want to just identify on the graph where we're focusing. The right-hand side of the function is really kind of growing, increasing up into the upper reaches of quadrant 2, which tells me in the y direction it's headed towards positive infinity. And that's how I'm going to finish my function behavior statement. As x approaches -3 from the right, y approaches positive infinity. So that completes the task for this first example. Just to recap, we did not have any removable discontinuities because there was nothing to factor or cancel. I did have an infinite discontinuity at -3, and that allowed me to describe the behavior of the graph from the left and from the right as it approached that discontinuity. Let's take a look at a second example. So here our function is more involved. It's f of x equals x cubed plus x squared minus 6x all over 4x squared minus 16. So again, I'm going to go into my process because really the tasks are the same. I want to identify removable or infinite discontinuities, and then I want to describe the graph's behavior from the right and the left. So let's find if there's any removable discontinuities. And the nice thing is that our approach, our strategies are the same. Removable discontinuities, we are going to factor any polynomial in the denominator or the numerator. Factor polynomials. And once we see the factorization, we're looking to see if I have any identical polynomial factors above and below that can cancel. So we'll jump into that. So from my numerator, this is a cubic, but what I notice is that there is an x term in each of these terms, an x factor rather in each of these terms. So what I would do first is factor out that x. So it's going to reduce the power of each one by 1. So that will be x squared. This is what's left, plus x minus 6. Once I do that, I see that I have a trinomial quadratic, x squared plus x minus 6, that itself could be factored. So remember what I'm looking for with the quadratic, I'll place 2 x's. That would give me x squared if I multiplied back. And then I'm trying to decide what would multiply to -6, that's my c term, and yet at the same time add up to my b term. It's not really written as a number. I could supply a 1. So it multiplies to -6, adds to +1. So what would work for us here is 3 and -2. 3 times -2 is -6. 3 plus -2 is 1. And I'm going to place those factors. So at that point, numerator is fully factored. Let's do the same for the denominator. So a different structure down there, 4x squared minus 16. What I do notice is that my two terms share a factor of 4. So I'm going to start with that factorization. And that will leave us x squared minus 4. X squared minus 4, again, is a factorable quadratic. I can use the difference of two squares pattern. So x plus 2 times x minus 2. And that completes the factorization of the denominator. At that point, what I'm looking for is identical factors above and below. And it turns out that I've got an x minus 2 that's both in the numerator and the denominator, and that identifies for me a removable discontinuity. So I'll go ahead and factor it out of the polynomial, out of the rational function, but I want to say where is that discontinuity. So just like we do with the denominator for vertical asymptotes, I'm going to take that canceled factor set it equal to 0, and solve. So for this example, we're going to add 2, and that would give me the location of x equals 0. I'm sorry, x equals 2 for a removable discontinuity. And we can see that clearly marked on our graph. It's really kind of emphasized there with this open point. And basically, when you have a cancellation like that, the way it appears on the graph is as a gap or a hole. So it's not a vertical asymptote. It's really a missing point in the curve. We'll come back to that to decide the end behavior. But let's investigate to see, do I have any infinite discontinuities? So remember, infinite discontinuities have to do with setting the denominator equal to 0. Now, we find the removable discontinuities first because when we go to find infinite discontinuities, we're going to work with the simplified version of the function. So I'm not going to go back to the original. What I want to take is this version, f of x equals, and I'm going back to that, really this version after I had canceled x minus 2. So what's left in my numerator is x times x plus 3, and in denominator 4 times x plus 2. I don't want to include that canceled x minus 2 because I've already identified that that's a removable discontinuity. So infinite discontinuity, remember from our previous example, you take the denominator, so in this case 4 times x plus 2, and set that equal to 0. And then I want to solve that. So here I'm going to divide by 4, and it kind of gets swallowed up by the 0. On the left, we have x plus 2. 0 divided by 4 is still 0. And then to solve for x there, I just need to subtract 2. And I get this small equation, x equals negative 2. And that, I can see, is a vertical asymptote. So there at negative 2, I've got a vertical asymptote, my infinite discontinuity. So we've completed the first task. We identified algebraically that I got 2 discontinuities, one removable, one infinite. What I need to do now is write the behavior of the graph as it approaches from the left and from the right. Let's start with our infinite discontinuity, since that's the one we can pretty much read off the graph. So let's start by considering the left behavior of the function. So recall, we'll write that, we'll put this in green so that it stands out. As x approaches, so here I'm going towards that value of negative 2. From the left, I put the minus superscript. And there I'm going to look on the left side to see what's the function doing. So there the function is increasing as it gets close to that vertical asymptote, headed up towards positive infinity. And that's how I would end the behavior statement. Y approaches positive infinity. We'll also look at the right side. So notice the function there is decreasing more and more and more as it gets close to negative 2 from the right side. And that looks like it's headed towards negative infinity. So the way I would record the right-hand behavior of the function around that infinite discontinuity is as x approaches negative 2 from the right, I'll put the power of plus, y approaches negative infinity. Please notice, if you got an infinite discontinuity, y is going to head towards infinity or negative infinity. That should match. The words should match the symbols. It's different for a removable discontinuity. So as I look now at the removable discontinuity, I see that the left and the right side are really headed towards the same y value, and it's not infinite, it's an actual number. So the question is, how do I find the number? Because if I were to plug in positive 2 into my original function, it would be undefined. So to find that y value, what I'm going to do is take my simplified function, so I'll circle it here, And that I want to plug in positive 2. That should give me the number that I'm looking for the y value. So f of 2 is going to be 2 times 2 plus 3. So notice I'm not including that x minus 2 factor. That's what would make it undefined. But I'm using the factors that are left. Over 4 times, in parentheses, x plus 2. I'll replace x with 2. And that I need to simplify. So that's going to be 2 times 2 plus 3 is 5. So 2 times 5 is 10. Over 4 times 2 plus 2 is 4. 4 times 4 is 16. If I reduce that down by dividing 2 out of the 10 and the 16, we get 5 over 8. So what I could say is that although that coordinate has a gap there, if it didn't, it would be the point 2 comma 5 over 8. Why do we do that? It helps me at that point to write the left and the right behavior of the function around that removable discontinuity. So we'll do that here. Again, we would record it as x approaches. So the removable discontinuity is at 2. From the left would have the power of negative. Y approaches 5 over 8. From the right-hand side, as x approaches 2 from the right, power plus, y also approaches 5 over 8. So kind of the bottom line there is if you've got a removable discontinuity, you're going to be approaching the same y value from the left as from the right. And that indicates that it's not a vertical asymptote. It's not headed to infinity or negative infinity. It's really a gap or a hole in the graph, really a point missing there. So thank you for joining for this investigation of finding discontinuities in rational functions. Let you find your own discontinuities in your rational functions. See you soon.